Why does SEM fail at atomic level defect identification? Imagine trying to see tiny details so small they are almost invisible. That's what scientists face when using scanning electron microscopy to find atomic defects. It sounds simple, but it's actually quite tricky. SEM uses a focused beam of electrons to scan the surface of a sample. When these electrons hit the surface, they produce signals that create detailed images of the surface topography and composition. But here's the catch. The resolution of SEM is usually between 1 and 20 nanometers. That's too big to see individual atoms or tiny defects at the atomic level. The reason is that the electron beam spot size and the interaction volume inside the sample are both larger than the space between atoms. When electrons scatter inside the material, they spread out over a larger area, causing the image to blur. So, instead of sharp atomic details, you get a smudged picture that shows the surface shape but not the tiny atomic imperfections. Another limitation is that SEM is a surface imaging tool. It can tell you about the shape and texture of the surface, but it cannot see inside the material to observe atomic arrangements or point defects like vacancies or dislocations. To see those tiny features, scientists turn to transmission electron microscopy or scanning transmission electron microscopy. These techniques send electrons through very thin slices of material, allowing 4 atomic resolution images. They also use special correction technologies to improve clarity and detail. Sample preparation also plays a role. SEM samples need to be conductive or coated with a thin metal layer to prevent charging. This coating can sometimes obscure or alter the atomic features you want to see. Plus, the high vacuum environment required for SEM can cause changes in delicate samples, making atomic-level defect detection even harder. When it comes to failure analysis, SEM is excellent for spotting cracks, corrosion, or surface contamination. But if you need to find the exact atomic defect that caused a failure, SEM falls short. Instead, scientists use transmission electron microscopy or scanning transmission electron microscopy because they can directly visualize atomic arrangements and pinpoint tiny defects that start the failure process. In summary, SEM cannot reliably identify atomic-level defects because its resolution is limited by the size of the electron beam and the interaction volume inside the sample. It mainly provides surface images rather than internal atomic structures. The preparation process and the physics of electron interactions prevent SEM from seeing at the atomic scale. Still, SEM remains a powerful tool for understanding larger surface features and failure mechanisms, helping us trace the origins of many material problems.